So the first survey questions that I asked you were just a little bit of vocabulary and a little bit of basic sort of getting your sense of how to use cycle notation to achieve a permutation. So this permutation, 1, 4, composed with 2, 3, 5, is that a permutation, a cycle, a transposition? Which of these answers did you say?
A.
We can call that a permutation, but we can't call it a cycle. Why can't we call it a cycle? What is a cycle? Each individual thing I'm putting in parentheses is an example of a cycle. So this 1, 4 here is a cycle. This 2, 3, 5 is a cycle. Because after all, what does cycle mean in the first place? It means one of these permutations in which every position is just sort of moving one step to its right around a big circular table, is one way to think about what a cycle is and why we call it a cycle in the first place, right? For example, this permutation that turns share into hairs, right? I can write down notation for this like this, 1, 5, 4, 3, 2. Why? How do I know it's 1, 5, 4, 3, 2? Where could I get that from? How would I get this notation for that permutation? So I could get this notation by starting in position 1, that's the letter S, right? And finding out that the letter in position 1 moves to position 5. So just to help myself out here, I'm going to label my positions above and below here. 1, 2, 3, 4, 5. So the letter in position 1 ends up going into position 5. So 1, 5. And then the letter that was in position 5, so I'll go directly up here, which is the letter E, that letter ends up in position 4. So 1 goes to 5, goes to 4. The letter in position 4 is R. It goes to position 3. So 4 follows 3. And then 3 goes to position 2. 3, 2. And then the letter in position 2, the symbol in position 2, goes back to position 1, and that completes the cycle, right? So around this table, if all of these positions took one step to their right, 1 would go to 5, would go to 4, would go to 3, would go to 2, would go back to 1. So that's why we call that kind of permutation a cycle. What did you find out was a way of representing this permutation that sends post into tops? Was there a way to represent that with a single cycle?
Yeah.
What was it?
1, 3, 4.
1, 3, 4. The P goes from 1 to 3, then the S goes from 3 to 4, and the T goes from 4 to 1. And so we've completed that cycle. And when you applied that permutation, 1, 3, 4, that cycle, to post, you get tops. When you applied it one more time, what did you get in sigma squared? What came after tops?
Soft.
Sopt, S-O-P-T.
Yes.
And then when you applied it one more time, post. And so what at that point were you ready to conclude? In this part of the daily work?
The order's 3.
The order is 3. Order of this sigma, the order of the cycle 1, 3, 4 is 3. Because what permutation is sigma to the third power equal to? The identity. And depending on which author you read, some authors will call the identity permutation, they'll just denote it by an epsilon. I don't know why epsilon. Epsilon like an E, except Greek. Or the way that I usually like to represent the identity permutation is just in an empty cycle, like this. You know, whichever way you like to write it, it's just a notation for the identity. The identity element in this group. Right? And how do we know it's the identity element? Post. Because it does nothing to any of the 4 positions. Every position ends up exactly in the same place where it started. And using the round table metaphor, I think it also makes sense why 1, 3, 4 should have order 3. Because 1, 3, 4 is nothing more than a permutation which tells every one of these positions to take one step to the right around the table. So then what is sigma to the second power going to do? If I apply this permutation once and then again, what's the net effect going to be around this table? 2 steps to the right instead of 1 step to the right. So sigma squared is going to send 1 to 4. It's going to send 4 to 3. And it's going to send 3 back to 1. Okay? So sort of 2 steps around the table. But 2 steps to the right around this table is also equal to what? one step to the left, which is another name for the inverse of sigma. Right? After all, the opposite of taking one step to the right had ought to be taking one step to the left. Right? Those two things cancel one another out. And so, from that point of view, what is sigma to the third power? What would it be asking us to do? 3 steps to the right. Well, when any one of these positions takes 3 steps to the right, it ends up exactly where it started. And from that perspective, we can understand why it's equal to the identity. So the order of this 3 cycle is 3. Yeah. So that's another thing we can take to the bank, right? That if I'm just looking at a single cycle, the order of a cycle is just going to be equal to its length. Okay? How many positions there are in my cycle. For this 5 cycle, it takes me 5 steps to the right around the table before I get back to my original seat. Let's suppose I want to know what the inverse of this 5 cycle is going to be. 1, 5, 4, 3, 2. How could I find the inverse of this? Is there a quick way?
To the right, everything.
Instead of taking 1 step to the right, I want to take 1 step to the left. That means read the same cycle backwards. Here's a place where I want to read the cycle backwards, right, from right to left, because now everything's going to be taking 1 step to the left. I'm going to start with position 1 again, because we try to always start with the lowest number position just by convention in a cycle. We don't have to. It's not wrong if we don't, but just for convention's sake, I'm going to start with 1. And when I take 1 step to the left, what am I going to be at? 1 step to the left is going to, it's going to get me over to 2. So my inverse is going to send 1 to 2. And then 2 is in turn going to be sent to 3, which is going to be sent to 5, which is going to be sent back to 1, which means our cycle is done. Right? So there's a quick way to read off the inverse of a cycle as well. Just read the cycle backwards from right to left instead of from left to right. Because now, again, the inverse is just taking 1 step to the left around this table, which again is going to have order 5. After all, we know that every element in a group and its inverse have the same order anyway. And so in particular, that's true for our cycles. And the one kinds of cycles that get special names, as we mentioned earlier, were the 2 cycles, where I'm just trading 2 spots. We call the 2 cycles transpositions. They have a special role to play as we go forward. So cycles are friendly and useful and important because every permutation can be written as a product of disjoint cycles. And disjoint just means that those cycles are not, they're not permuting, they're permuting sets of symbols that are disjoint. Right? So one cycle acts on a subset of symbols that the other one does not act on, and vice versa. So if I look at this permutation right here that sends alert into later, if I got cycle notation for this, again labeling my positions 1, 2, 3, 4, and 5, I would be here sending position 1, A, into position 2, and position 2 gets sent back to position 1. So 1 and 2 in this cycle are getting transposed. So I'd write that in cycle notation as 1, 2. And then meanwhile, what's happening in the other positions? 3 is going to 4. 4 in turn is going to 5, and 5 is going to 3. And so I have another cycle, 3, 4, 5. And what do we notice about these 2 cycles, 1, 2, and 3, 4, 5? They're disjoint. They're totally separate from one another. It's like there's this wall that the 2 of them are not crossing, right? The first cycle, 1, 2, is only affecting the first 2 symbols, symbols 1 and symbol 2. The second cycle is only affecting symbols 3, 4, and 5. And so they have no symbols in common. They don't make a common claim on any of these 5 symbols. And so we call these 2 cycles disjoint from one another. And because they're disjoint, it doesn't matter if I do this permutation before that one or that one before this one. The result is going to be the same because they're not interacting in any way. And so those are going to commute one with another. So 1, 2 composed with 3, 4, 5 is the same as 3, 4, 5 composed with 1, 2. So that's what we mean by disjoint cycles. And every permutation can be written as a product of disjoint cycles. And how you can do it is just by following this algorithm that we kind of used here to find cycle notation for this permutation. Just figure out where the symbols go. Once you get to the end of a cycle, close out that cycle and start a new cycle. And by doing that, you're always going to come up with a product of disjoint cycles to represent your permutation. Of course, one of the challenges about permutations, I talked about this with a couple groups, is that the way that we express a permutation using notation is not necessarily the same. If you and I write different notation, it can still represent the same permutation. For example, 345 is a way of representing this permutation, but so too would be the composition 3534. Those two are different notation, but they are the same permutation as one another, right? So this gives us sort of a way of simplifying expressions, if you like, inside of the symmetric group. These represent the same permutation, the one that sends ERT into TER, just using different notation, one for another. I'm going to talk about this third survey question next. If this permutation, 135, 2354, acts on the word stone, what is a quick way to figure out where the letter O ends up in the final product? First of all, what did you say for the answer here? Which position does letter O end up in? First position. And how do we know? What is a way of figuring that out? Yeah, Kelly.
After doing the whole thing, you can see that O starts in the third position.
O starts in the third position.
3 goes to 5.
3 goes to 5, so I know that this O is going to end up over here in position 5 after the first cycle. And by the way, the first cycle is this one, remember, because we're reading this composition of cycles from right to left. Right, so the O ends up in position 5 after one step.
And then if you look at the next cycle, 5 goes to 1.
5 goes to 1. Yes. So then in the first cycle that's written here, 5 wraps back around to 1. And so this fifth position in the second step is going to end up in the first position here at the end. Right. So that's the quick way of tracing what happens here. It starts in position 3, ends up in position 5 after this cycle does its thing, and then 5 goes to 1 when this cycle does its thing. So the net result is that 3 goes to 1. Did anybody do the whole action of this permutation on the word stone? What did you get at the end?
Onset.
Onset. Yeah, that ends up being another actual anagram of the word stone. If we wanted to simplify this product into a product of disjoint cycles, we would have to trace where every one of these things ends up going. Position 1 starts with my S here. Well, 1 goes nowhere in this cycle, but then in this cycle, 1 goes to 3. And so my product is going to begin with 1, 3. And then I would ask, where does 3 go? Well, as we just established, 3 goes to 5, which goes to 1. And so because 3 goes back to 1, we'll finish the cycle, 1, 3. Then we'll move on to the next symbol that we haven't figured out yet, which is position 2. Where does position 2 go in my first cycle? 2 goes to 3, which then in my second cycle goes to 5. So the net result is 2 goes to 5. So then where does 5 go? 5 is my E. 5 goes to 4, which goes to, it stays, right? So 5 goes to 4. So my cycle continues for the 4. And then where does 4 go? 4 goes to 2, and then 2 stays put. That concludes my second cycle. So in other words, this product of 2 non-disjoint cycles up here at the top is actually equal to that product of disjoint cycles down here at the bottom. And what's fantastic about that is it's when we have a product of disjoint cycles that we can actually understand a permutation best. The best way to understand a permutation is to write it as a product of disjoint cycles for the following reason. So once we've written a permutation as a product of disjoint cycles, each cycle being one of these things, right? We can then use that information to determine the order of a permutation. Kelly?
I just have a question.
So let's take this alert permutation that we were looking at a minute ago, which has this 1, 2, 3, 4, 5 composition. So this is not a cycle, but it is a product of 2 disjoint cycles, one of which is a 2 cycle and the other which is a 3 cycle. So those two combine together to give what I call the cycle type. So this is a permutation that is a composition of a 3 cycle and a 2 cycle. So I'll call it 3 plus 2. Now, why does it make sense? Well, let me ask this. It's already up on the screen. But why does it make sense that the order of this permutation should be 6? Why does it make sense that it should take 6 applications of this permutation before we get back to the identity. How often does the A and the L come back to its original position as I continually apply this permutation? Every 2 times. So whenever my exponent is a multiple of 2, my A and my L are back to their original positions, right? Here, 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 and here. But what about the ER and T? When do they come back to their original positions? How frequently?
Every third.
Every third. And so when are all of my letters going to be back in the positions that they started? After 6 times, because 6 is a common multiple of 2 and 3. Right? So anytime my exponent is both a multiple of 2 and a multiple of 3, all of my letters will have come back to their original positions. And so why is the order equal to 6? Because 6 is the first time that happens. It's the least common multiple. Exactly. The smallest positive number that's both a multiple of 3 and a multiple of 2 is going to be equal to the order of this permutation, because that's the first time that all of my symbols are going to have come back to their original positions. Right? So once my permutation is written as a product of disjoint cycles, we can find the order of that permutation by taking the least common multiple of the orders of the cycles themselves, which is the same thing as the cycle length. Right? So as soon as I know what the cycle type of a permutation is, that completely determines the order. That also means that any 2-cycle composed disjointly with a 3-cycle will have order 6. So it doesn't matter that this is 1, 2, 3, 4, 5 instead of, 2, 5, 1, 3, 4. Right? As long as the cycle type is the same, that determines the order, the least common multiple of the cycle lengths. Finally, how many elements does S4, the group of permutations of 4 symbols, have? 24. Why? What's the underlying principle here? Yeah, 4 factorial. There are 4 factorial. There are 24 different ways of permuting the elements of a 4-element set. Because there's 4 different places where I can put the letter P. But then once I put that letter there, I have 3 places where I can put the letter O. And then I have 2 open spots where I can put S, and then I have only 1 place that T can go at the end of the day, right? So since those choices are independent, the total number of options is 4 times 3 times 2 times 1. 4 factorial. Okay, great. So one of the things that I didn't expect to happen in our activity on Friday, but I'm actually really delighted did happen, was that when I asked your groups to think about how do we understand cycle notation, like 1, 5, 4, 3, 2, how do we understand what this cycle means? One of the groups, I think it was the Diamonds group, suggested a way of understanding what this cycle means using swaps. And so what you said was something like swap 1 and 2, and then swap position 1 and 3, then swap position 1 and 4, and then swap position 1 and 5. So thinking about what this notation means in terms of just swapping 2 positions at a time. Right, 1 and 2, then 1 and 3, then 1 and 4, then 1 and 5. And that's true. But what that does is not only give us a way of understanding this notation, it gives us a way of rewriting this 5 cycle as a product of 1, 2, 3, 4, 2 cycles. Because to swap 1 and 2 is to apply what cycle? 1, 2. To swap 1 and 3 is to apply 1, 3. And so on, and so on. Right? And so from the perspective of the symmetric group on 5 symbols, right, the group of permutations of 5 symbols, this 5 cycle and this product of 4... Wait a minute, do I have this written backwards? So now I'm second-guessing myself. Let's check. We need 1 to go to 5. Well, here 1 goes to 2, but then 2 doesn't go anywhere. So I actually have this written backwards. My apologies. And it means I have the thing underneath written backwards as well. Swap 1 and 5. Then 1 and 4. Then 1 and 3. Then 1 and 2. And now when I write this product of cycles, it goes the other way. 1, 5, 1, 4, 1, 3, 1, 2. Right. So what I'm saying is that the same permutation that sends share into hairs, right, that's one element of the symmetric group of 5 symbols. And it has these 2 different expressions. I can express it as a 5 cycle, or I can express it as a product of 4 2 cycles, product of 4 transpositions. Right? And that is what leads us to our last point about permutations, is that every permutation that can not only be written as a product of disjoint cycles, it can also be written as a product of just transpositions, just two cycles, using that same sort of process, that same idea that we just used. And it turns out that that product is not necessarily unique. If I go back a tick here, put this back up for a second. I could find a different way of expressing this same cycle as a product of transpositions. If I, for example, added, I don't know, let's say I added another 1, 3 right here, and then I added another 1, 3 in front of it. So let me stick 2 more transpositions on the front. How do I know that I still have the same permutation as I had a minute ago after I add these 2? Ashley?
Because you would switch 1, 3 to begin with, but then you switch those 1, 3 again and they go back.
That's right. I would switch 1, 3 and then switch them back. So 1, 3 composed with 1, 3 is going to give me what permutation? 1, 3 composed with 1, 3 is going to be identity. So they cancel one another out. So my point there is to say that we can express the same cycle as a product of transpositions in a variety of different ways. But one thing that is the same between those 2 different expressions is that on the one hand, I have 4 transpositions expressing this. On the other hand, I have 6. So those are different numbers. But those 2 numbers are at least both even numbers. And it's kind of a tricky theorem to nail down. So we're not going to look at the proof. You can certainly look it up in our textbook. But the expression of a permutation as a product of transpositions is unique up to the parity of the number of transpositions used. So you and I might come up with different lists of transpositions to represent a given permutation, but either both of our lists are going to have the same, either both of our lists are going to use an even number of transpositions, or both of our lists are going to use an odd number of transpositions. I can't have an even and you have an odd number of transpositions in your list for the same permutation. And so what that means is that the evenness or oddness of how many transpositions are needed to write down a given permutation is an invariant of that permutation and not of the expression of that permutation as a product of disjoint cycles. That was the paragraph. All of which is to say the following: that when I express a permutation as a product of transpositions, the number of transpositions that I use, its evenness or its oddness is well defined. And if the number that I use is an odd number, as is in this example, I can take this 3, 4, 5 and write it as 3, 5, 3, 4. If that number is odd, then I call that permutation an odd permutation, quote unquote. If it's even, I call it an even permutation. And the subset of even permutations actually forms a group called the alternating group. So the alternating group is nothing more than the set of all even permutations. Even meaning we can write it as a product of an even number of transpositions. So here's another classic place to get confused. And that is that an even permutation is not the same thing as a cycle of even length. For example, a single 2 cycle, like 2, 3, that's a cycle of even length. But it is an odd permutation because it can be written as a product of 1 transposition. So something to keep straight for yourself is that the k cycles are even permutations when k is odd, and are odd permutations when k is even. So put that in your e-pen and vape it. So yes, our algorithm for writing out the transpositions that I can use to represent something like 3, 4, 5. Notice how I got 3, 5, 3, 4. Is I took my first position and my last position and put them together in a transposition, and then I moved back 1 position and got my second, and then I was done. So in fact, I guess one way of doing this is a k cycle can be written with how many transpositions? I wrote my 3 cycle using 2 transpositions. A 2 cycle is itself 1 transposition. Our 5 cycle from a minute ago, we wrote with how many transpositions? 4. So what do you think the general principle is here? K minus 1. That's why the evenness and oddness between cycle length and transposition number flip-flops. And the set of all even permutations forms a group called the alternating group. And exactly half of all permutations are even. The other half are odd. Here's a question. Why is the set of odd permutations not a group? Let's think about inverses first. If you give me an odd permutation, what can I say about its inverse? Like let's say 1, 3, 4. That's an odd permutation. What's its inverse as a permutation? 1, 4, 3. Is that odd? Yeah, that's odd. So the inverse of an odd permutation will still be an odd permutation. What about closure? If I take 1, 3, 4, odd permutation, and I compose it with 1, 3, 4, odd permutation, what am I going to get? That turns out to be 1, 4, 3 again, which is also odd. Wait a minute here. Oh, I've got a typo, don't I? Sorry, 1, 3, 4, 2. Let's make that our odd permutation here. So its inverse will again be an odd permutation, because the inverse of a k-cycle will always be a k-cycle. Right? When I compose it with itself, though, 1, 3, 4, 2, what am I going to get if I compose 1, 3, 4, 2 with itself? Let's check it.
1, 4.
So, right, 1 is going to go to 4, because 1 goes to 3, and then 3 goes to 4. Where is 4 going to go? It's going to go to 2, which is going to go to
1.
And so that closes my cycle. What about 2? Where does 2 go? Goes to 1, which goes to 3, so 2 goes to 3. Then where does 3 go?
Back
To 4, which goes back to 2, closing that cycle. Okay. So 1, 3, 4, 2 was an odd permutation. I multiply it by itself, compose it with itself, I get this. What kind of permutation is 1, 4, 2, 3?
Even.
It's even, because it's a product of how many transpositions?
But what makes it odd? You said it wasn't odd.
It's odd because it's a 4-cycle, and I can write it, therefore, as a product of 3 transpositions. I can write it as 1, 2, 1, 4, 1, 3. But when I compose it with itself, I get an even transposition. So odd composed with odd gave me even, just like an odd number plus an odd number gives me an even number. And then finally, what about the identity? What kind of a permutation is the identity permutation? Even or odd?
Even.
It's even. How do we know? So I can write it as a product of 0 transpositions, or 2 transpositions, like 1, 3 composed with itself, right? So since the identity permutation is even, that's probably the most glaring reason why the odds can't form a group, but the evens can.